now it's time to thank the participants of this school and welcome to everybody to share this week on dynamical systems. And first, I would like to thank the scientific committee for this meeting and also the organizing committee. And a special thanks to Leticia, Sueli, and all the people that work to make this possible from the strategic point of view in the organization. And we have also to thank the financial support from IMPA and CNPq, FAPERJ, and CAPES. Okay, it was possible to make this happen this week. Okay, and I would like just to start with giving a historic of all this is the 8th meeting or school on dynamical Brazilian dynamical school, and then I will present the historical of all the other ones that we had in the past. We started, the first one was in Maceió, in the Federal University of Alagoas, and it was organized by Keller de Oliveira, one of our friends and the dynamicists, and this happened in 2010. And we had there, this was the mini courses, and the one point that I would like to talk to you is this kind of school. We decided that it was a little bit different from the other areas, in the sense that we always have mini courses just to attract the people to the area, okay? And this was in 2010, and then I have some pictures in this from this meeting there. This is Federico Rodrigo Hertz. This is Vitaly Egerson, that they gave mini courses during that occasion. And this is a photo with the students. Unfortunately, it's too light here. We cannot see quite sharp the slides, but okay. Yes. Yeah. Indeed, in this school, I see, look, this is the group of students in this meeting, and there are many people here from my university, indeed. We always have the big involvement of our students in this kind of schools. And this is Jaqueline Siqueira, and there are some other ones here. The second one was in São Carlos, and indeed it was celebrating my 60s. And you see that one thing that was in 2012. And one observation is Cristina Lizana made an observation that, you know, that in this organizing committee and in the scientific committee, there is no woman, only men. Nowadays we have more. Okay, so this was the group picture from the meeting there in São Carlos. You know that, see, all this, the number of participants is huge. And Catherine is giving a course, and what happened at this occasion is that it had some broken the energy there in the institute, and then the solution was to give a class for the mini course in the patio outside of the instead in the auditorium. This is Catherine that is giving class, and here is some pictures that, okay, here is only Sarigi, that he gave a course there. And here is Sarigi, me, and Artur Lopes. And this is Gododesk, Anton. And here is Jabuticaba. Who, no, the point is that when we went to the, for the dinner, the conference dinner, this was the picture was in the near in the restaurant in the country, and everyone was taking jabuticabas instead of it was better than the I don't know. Everyone was there, and I remember that Edson, não Edson, era André de Carvalho, he was here taking jabuticabas and distributed to everyone. And okay, then the third school was in Bento Gonçalves in the south part of Brazil. And this region is famous for wines. That's why you have here. This was drawing for someone there. And again, we had mini courses by Juan Rivera, Sylvain Crovisier, and Ferran Valdez. And this is, again, the group picture from the people in this meeting there in Bento Gonçalves. We stay in a nice countryside, the hotel, nearby, how you say this, cantina for wine. And okay. And we have, this is Daniel Ismania. He was giving a class, a lecture there in this meeting. And the one thing interesting is that I put this, it's not possible to see, but he's using the same tissue. But that he used here. Look, he was here. You cannot see the T-shirt that he is using in 2000. And then I put on purpose, but he told me that he already throw away this skirt, and no more repetition. And this one was the fourth school. And onde que foi isso aqui? In Campinas. That was in Campinas, and in a region near, not downtown Campinas, but in Valinhos. It's a city nearby Campinas, and there is some place, it's like in a hotel for workers. Somehow they could find a place to everybody was in the same hotel there. And here is the group picture there in Valinhos. This time we had Pierre Berger, who was giving a course, and some other ones there. And finally, this was the fifth school in Minas Gerais, organized by Karina and the team there. And this was in 2019. And okay, here is the group picture. You see that the number of participants is always increasing and increasing. And here is I like this picture. And with everyone from my university there, my students, and me, Jaqueline Siqueira, Alexander Arbieto, Catherine, and the other ones are students from my university that they were participating in this school there. And now that was during the pandemic, and unfortunately it was online, no? And the celebrating the 60th of Lorenzo, and this is the group picture in the what we could do during that time, and that was supposed to happen in Fortaleza, but then it was online, and that Yuri organized the seventh school in Fortaleza, and this time it was how you say this, presential, everybody there, and here is the group picture there in Fortaleza. And finally, okay, that I think is all. And let's start the activities of this one. Okay. Okay. Okay, and then the first talk in this school, it will be by María Isabel Cortez from University of Chile. And she will talk about subshifts, invariant measures, and residually finite groups. Please.
Okay, thank you for the invitation. It's an honor for me to be here. Ah, ¿hacia dónde tengo que apuntar? Okay. So I'm going to give a very general talk. This is in the, this is part of what in dynamical system is known as symbolic dynamics. So this is, I'm going to try to explain some problems related to symbolic dynamics and maybe related to group theory. This is more or less the place where I live in mathematics. So I'm going to start explaining which are the objects with I work. And first, I need a group, an infinite group, countable group in general. For example, the integers, C squared, a free group with two generators, the rational, any infinite countable group. And a dynamical system in this talk will be an action of this kind of groups on a compact metric space. And this action is an action by homeomorphism. So for every element of the group, we associate an homeomorphism. So this is the kind of dynamical system where I'm going to talk today. And in general, we work with dynamical systems or actions which are faithful. That means that the only element of the group that acts trivially is the identity of the group. And another way to think of this is saying that the group G, is a subgroup of the group of homeomorphism on the space X. So this is the general setup of this talk. And the typical example for this kind of dynamical system, one of the typical examples is the following. Suppose that you have a group like this, so an infinite countable group G. Every group like this admit a faithful action on the Cantor set, so on a compact metric space totally disconnected without isolated points. And how can we define this action? As follows. So suppose that you take sigma, a finite set of elements with at least two elements. For example, sigma can be the set that contains 0 and 1. And we take all the functions from the group G to sigma. This is the set sigma G. And we can think of the element of sigma G also like all the sequence of elements in sigma indexed by G. This is another way to think of this element. And there is a topology here. So in sigma, you put the discrete topology, and in sigma G, we take the product topology. And when you do that, you get a Cantor set. And there is a natural action of G on this set And this is just the shift action. So the action consists in translating the sequence of sigma g. So for example, if we take an element G in the group G and an element X in sigma G, Gx in the coordinate 8 has the same element that you see in the coordinate G minus 1, 8 of X. So we are translating the sequence by G. So it's not difficult to show that this is an action of the group G on sigma G, and every G define an homeomorphism. So this is a topological dynamical system in the sense that I defined in the previous slide. And it's also not difficult to show that this action is faithful. So for example, if you take an element X in sigma G, where all the coordinates are the same, except one coordinate, when you apply the action of an element different from the identity on this kind of sequence, you get something different. So this is a faithful action of the group G on the Cantor set. So this is one example of the kind of dynamical system that I'm going to talk today. The kind of questions that I would like to address are the following. So the kind of question that I would like to address are try to characterize the group G through the dynamical properties of the action that the group admits on the Cantor set. So we know that any infinite countable group admits a faithful action on the Cantor set, but I would like to be more precise. So try to distinguish the groups in terms of the dynamical properties. And I'm going to start with an example of that kind of question. This is a question that many people in dynamics and symbolic dynamics worked on. I don't work in that kind of question, but I think it's interesting to try to understand the kind of problems. Okay. So the action that I showed before, so the action of G on sigma G by the shift action. So this is a huge dynamical system, but we can identify some smaller dynamical system inside. And these kind of dynamical systems are called subshifts. So what is a subshift? It's just a closed subset X of sigma G, which is invariant by the shift action. So a subshift, if we take the restriction of the shift action on a subshift, we get a new dynamical system that we call also a subshift. So this is the kind of dynamical system that people study in symbolic dynamics. And when we have a subshift, we can identify some patterns of the sequence. And what is a pattern? It's just something that you define in a finite set. So you get, for example, F, a finite subset of the group G, and a pattern is just a function B in sigma F. So it's like the sequence, but in a finite, with a finite support. And we say that a pattern appears in an element X in sigma G if somewhere in the sequence X you see the pattern B. And when we understand this, we can define some special subsets. Suppose that you have a collection of patterns, a collection F of patterns. We can define X minus F, the collection of all the sequences X in sigma G, where the patterns of F doesn't appear. So the collection of all the sequence in sigma G, where F is the collection of forbidden patterns. This is another way to say this. And it's not difficult to show that a subshift is exactly a set of sequences with forbidden patterns in a specific set. So it's not difficult to show that set X in sigma G is a subshift if and only if X is equal to X minus F for some set of patterns F. So this is a combinatorial description of a subshift. And when we have this characterization of a subshift, we can identify a particular class of subshifts, and these are the subshift of finite type, the SFT. And what is a subshift of finite types? It's just a subshift that we can define from a finite set of forbidden patterns. And there are many things that we know about subshift of finite types. For example, if the group G is the integer, is it known that the subshift of finite type can be described by means of a finite graph? That means that for any subshift of finite type, there is a finite graph where the elements of the subshift of finite type are just the infinite path that you can obtain through the graph. And when we have this, if your graph is finite, there is always cycles in the graph. So in the subshift of finite type, when the group G is equal to the integers, the subshift of finite type always have periodic points. So in this case, point with finite orbit. But if we change the group, if we work with C squared, for example, this is not true anymore. So there are examples of subshift of finite type when the acting group is C squared, where all the points are aperiodic, so where all the points have a trivial stabilizer. And this is a very old result from Berger from '66, and this is related with the Wang tiles. If you are familiar with this, these are just examples of Wang tilings. And this kind of situation, so we see that there are two different behaviors of subshift of finite type depending on the acting group. So this kind of behavior start to so we start to ask questions about this. So what can we say about the subshift of finite type depending on the acting group? And there are some results, mainly from Emmanuel Rondel and Cohen, where they relate the existence of strongly aperiodic subshift of finite type with some combinatorial properties of the group. And these properties are related to the number of ends of the group and also related with the decidability of the word problem. So if you are not familiar with this, so the number of ends, it's just, any finally generated group can be described by means of a Cayley graph. And the number of ends is just the number of connected components that you obtain when you take off some neighborhood of the identity of the group. So for example, the integers, how is the Cayley graph of the integers? It's just a line. So what happens when you take off a neighborhood around 0? You obtain two connected components. So in that case, the group has two ends. In the case of C squared, you have only one. In the case of the free group, you have infinitely many. And there are some results that say that if you have a subshift of finite type, which is strongly aperiodic, the group has to have at most one end. And there is a conjecture. There is a conjecture that says that the group G admit a strongly aperiodic subshift of finite type if and only if the group G has only one end and have decidable word problem. So this is an example of a kind of problem that relate trying to characterize some properties of the group with some dynamical properties of the actions of the group on the counter set. In that case, about the strong aperiodicity of subshift of finite type. And the kind of question that I'm more interested in maybe are related with the try to understand what can we say. For example, with respect, okay, we fix a group G, and we would like to know how is the space of invariant measures of an action given by the group G. And for example, there is a very classical result that says the following. Then I'm going to explain a little more about the amenability. But this is a classical result. The classical result says that the group G is amenable if and only if any action of G on a compact metric space admit invariant probability measures. And this result can be improved a little. This was made by Giordano and De La Harpe in 1997. And we can say that the group G is amenable if and only if any action of G on the counter set, action by homeomorphism, admit at least one invariant measure. So if the group is non-amenable, for example, if your group is the free group with two generators, there are actions of the group of the free group on the counter set without invariant probability measures. And another kind of property that can be characterized by means of the set of invariant measures of the action of the group is this one. For example, this is a result from Glasner and Weiss from 1997, property T of the group, which is a property related with the representations of the groups. The group G has the property T if and only if the space of invariant probability measures of the shift action of 0, 1G is a Bauer simplex. Bauer simplex means that the set of ergodic measure is closed. And we know, for example, that if the group G is equal to the integer, this space of measure is the Paulsen simplex. So this is like the opposite. So there are some properties of the group that can be characterized by means of the dynamical properties of its action. So this is the idea of the kind of problem that I would like to talk today. Okay, and in my case, I'm going to focus in a particular family of groups, the residually finite groups, and there are several ways to define residually finite groups, but maybe the simplest definition is the following. So we say that a group G is residually finite if the intersection of all its subgroup of finite index is trivial. So residually finite groups are groups with a lot of finite index subgroups. And this is equivalent, for example, to say that for every element different from that entity, we can find a finite group F and a homomorphism from the group G to F, sending this element to some element different from the identity. This is also equivalent to the existence of decreasing sequence of finite index subgroups with trivial intersection. And this is also equivalent to the same, but taking decreasing sequences of normal finite index subgroups. So these are equivalent ways to say that a group G is residually finite. So for example, the integers are residually finite, C squares is residually finite, free group with D generators is residually finite. What kind of groups are not residually finite? For example, the rationals. So if you try to define a homomorphism from the rational to some finite group, you will get something trivial. So I'm going to be more in this side of the groups. And why I'm going to focus on residually finite groups? Because these groups have very nice properties. For example, residually finite groups, they can be embedded in compact, totally disconnected metric groups. and embed in order that the embedding is dense. And how can we do that? It's not complicated to do that. For example, if the group is residually finite, we know that there exists a decreasing sequence of normal finite index subgroups with trivial intersection. If the sequence is decreasing, for every n, there is a natural homomorphism from this quotient. So I take the class of G with respect to the group gamma n plus 1, and I send this class to the class of the same element with respect to gamma n. Because the group are, the sequence is nested, this is a well-defined homomorphism of groups. And when we have this, we can define an inverse limit. So we can define the subgroup of the product of this finite group with the property that every element of H has the property that the coordinate n plus 1, if I apply the homomorphism to n, I get the coordinate n. So the inverse limit using this family of homomorphism. This is a compact group, totally disconnected, and it's easy to define a homomorphism from G to H. And the image of G by this homomorphism is dense in H. So this is a compactification of our residually finite group with a compact group which is metric and totally disconnected. So this is a nice property of the residually finite groups. And from this, we can give a dynamical characterization of residually finite group. We can characterize residually finite group in the following way. We can say that the group G is residually finite if and only if there exists a minimal, equicontinuous, and faithful action of G on the counter set. Minimal means just that the orbits are dense, and equicontinuous, it's just by isometries. So an action of G by isometries, faithful on the counter set. So the existence of an action like this is equivalent to say that the group is residually finite. And why this is true? Because the equicontinuous action, the minimal equicontinuous action on the counter set are just of this kind. So they are given, the phase space are given by inverse limits, like the previous one, but maybe where the groups gamma n are not necessarily normal. And the action of G is just by left multiplication, coordinate by coordinate. And these actions are faithful if the intersection of the biggest normal subgroups in the gamma n's is trivial. So the existence of an action of this implies that the group is residually finite. And if the group is residually finite, you always can define an action like this. And these are exactly the minimal equicontinuous actions on the counter set. So this is a dynamical characterization of a residually finite group by means of the action that they admit. But another kind of question, this is not a subshift. If we think of the first example that I gave here, this is not a subshift, but I would like to give a characterization of this kind of group by means of the existence of some kind of subshifts. And we can characterize residually finite group by means of the existence of a particular family of strongly aperiodic subshifts. These are not necessarily subshift of finite type, like in the second example that I gave, but we can characterize a residually finite group by means of the existence of some particular kind of subshift. And in order to try to understand this, I'm going to assume first that we are working with G equal to the integers. I'm going to assume first that we are working with G equal to the integers to try to understand what kind of subshifts they are. So suppose that we are working with G equal to the integers. So here, sigma G is just sigma Z. So the B infinite sequence with of symbols of elements in sigma. And we are going to say that a sequence in sigma Z is toplet if every coordinate of the sequence is periodic with respect to some period that depend on the coordinate. So for every n in the integer, there exists some p such that what I see in the coordinate n is the same that I see in the coordinate n plus pk for every k in C. So the sequence is toplet if every coordinate is periodic with respect to some period, and this period depends on the coordinate. So an example of toplet sequence are the periodic sequence, but I will be interested in the toplet sequence which are not periodic. For example, here, if I fix this coordinate, we can see the same color every 3 spaces. So in this case, the period P is 3. And we can see that the other coordinates, they are periodic with a different period and so on. And from this kind of sequences, we can define a particular family of subshifts. We are going to say that a subset of sigma C is a toplet subshift if this is the closure of the orbit of a toplet sequence. The closure of the orbit are invariant and are closed, so they are subshifts. So a toplet subshift is just the closure of the orbit of some toplet sequence. And there are many things that we can say about these subshifts. They are very flexible. For example, it's not complicated to show that they are minimal. Why they are minimal? Because this property of that every coordinate is periodic with some period implies that if you fix a cylinder set, the return times to the cylinder set contains some finite index group. So the set of return time is syntactic. So this implies that the subshift is minimal. So every orbit is dense. So this is something that is not difficult to show. There are some other properties. For example, this kind of subshift, they are related to the minimally continuous system on the counter set that I defined previously. They are exactly the minimal symbolic almost one-to-one extension of these systems. Almost one-to-one means that you have a factor map. No. Inside of the toplet subject, you have things which are not toplets. If everything, there is some characterization. For example, toplet subshifts are a kind of point which are called regularly recurrent. If you have a minimal system where every point is regularly recurrent, this is an odometer. This is a key continuous. So here you have a lot of elements which are not toplets, and the behavior of the subject depends on how big is the space of toplet subshift. So sometimes this has, okay, they are invariant. So if you have an ergodic measure, this is zero measure or total measure. But when they have zero measure, there are any kind of behavior that define other dynamical properties of the subject. But not all the sequences are toplets there. Yeah, that's a good question. But we can characterize this subshift as the minimal almost one-to-one of the almost one-to-one extension of the odometers. So this implies, for example, that the maximal equicontinuous factor of toplet subshifts are the odometers. So the minimal equicontinuous system on the counter set. And almost one-to-one means that if you see all the sequences in the toplet subshift whose image has only one pre-image, this is dense. And these are exactly the toplet sequences, in fact. And on other kind of things that we can say, for example, inside the family of toplet subsheet, we can find all the possible values of topological entropy. Inside the family of toplet subsheet, we can find all the possible set of invariant probability measure. So if you fix a choked simplex, you can find a toplet subsheet having this simplex like as the set of invariant measure. And also we can combine all these properties. So you can fix the entropy, you can fix the set of measures that you want, and also you can ask questions about orbit equivalence that I'm not going to explain here, but you can fix parameters and you can find a subshift, a toplet subsheet having these parameters. So this flexibility, this kind of flexibility motivates the generalization of this kind of subsheet to group actions. And for group actions, if we want to try to define something similar, how can we define a period here? What is a period in the case of a toplet sequence when the group G is the integers? A period is an integer, but a period is defining a subgroup of the integers. So in the general setting, how can we define a toplet sequence? Now suppose that we are working with a group G, any countable infinite group G. So we say that an element X in sigma G is toplet if for every coordinate, so in this case a coordinate is an element of the group, for every element G in the group, there exists a finite index subgroup gamma, so this is the period, such that what I see in the coordinate G is the same that I see in the coordinates gamma G for every gamma in the group gamma. So a sequence in sigma G is toplet if every coordinate is periodic with respect to the elements of some finite index subgroup. So this is a generalization of what we had in the case of G equal to the integers. And again, in this case, a toplet subsheet will be a subset of sigma G, which is obtained as the closure of the orbit with respect to the shift action of a toplet element. The same thing that we had in the case of G equal to the integers. And again, it's not complicated to show that this class of minimal subshifts are minimal using the same argument. And now we can ask about this property of being strongly aperiodic. What do we need to get a toplet sequence which is strongly aperiodic? So here, suppose that we have this toplet sequence X. For every element G in the group, we know that there exists a finite index subgroup of periods, gamma G. And what happens if we take the intersection of all the gamma G? If we take the intersection of all the gamma G, we are going to see that this group, the intersection, is in the stabilizer of X with respect to the shift action. So this implies that if the sequence is aperiodic, so if the stabilizer is trivial, then this intersection has to be trivial. So the first thing that we can say, if there exists a strongly aperiodic toplet G subsheet, then the group has to be residually finite because of this property. And in fact, this is a characterization. It's possible to say that this is an if and only if. So there exists a strongly aperiodic toplet subsheet in 01 G, if and only if the group G is residually finite. So the existence of strongly aperiodic toplet subsheets is equivalent to say that the group is residually finite. So here we are this is a characterization of a family of group by means of special kind of subshift that they admit. So for example, there are strongly aperiodic toplet subshifts in 01ZD, in 01F2, for example, but there is no aperiodic toplet subshift in 01Q because the rational are not residually finite. And now, what can we say about the property? So what can we say about the property that we knew for the case of G equal the integers? In this case, most of the property are recovered. So for example, again, now if we work with any residually finite group, toplets subshifts for a group G are exactly the minimal symbolic almost one-to-one extension of the minimal action of G on the counter set. This is the same that we had in the case of the integers. And again, but here we need to ask for something more. If the group G is amenable and residually finite, it is possible to realize all the possible values of the topological entropy inside of the family of toplet G subshifts. And the same for the measures. So if we take G residually finite and amenable, here there is this property that appears. If the group G is residually finite and amenable, we can realize also all the possible set of invariant measures using this family of subshifts. And also there are some properties related to orbit equivalence that can we describe using this class of subshifts. So this family of subshifts that were defined at the beginning for the action of Z, they can be also extended to the action of residually finite groups, and we get more or less the same kind of properties. So they are flexible in the sense that you can realize any entropy, any measures, etc. But here there is something new that appears when we have these properties about realization. There is the amenability property about the group. And if we remember that amenable groups are characterized by means of the existence of invariant measures, one natural question is to try to see if it is possible, for example, to characterize the amenability of residually finite group just studying the invariant measure of toplet subshift, or saying in an equivalent way, if it is possible to find a toplet subshift without invariant measure when the group G is residually finite and non-amenable. So this is another way to ask the same. And I'm going to try to explain this question. This is just another characterization of toplet subshifts as model sets. So another way to characterize toplets elements is saying that an element is toplet, an element X in 0,1 to the G is toplet if and only if X is a model set with respect to some particular window in the odometer. I'm not going to go in the details, but this is useful if we want to construct toplet subsheet with more precise properties. Okay. So I'm going to try to explain the relation between residually finite groups and non-amenability using toplet subsheets. So this is just a definition. Here, an invariant measure for us is the same that for anyone in dynamical system. So an invariant measure of the topological dynamical system will be a Borel probability measure, which is invariant by the action of the group. And we are going to denote MXG, the space of invariant probability measures. What is the property of being amenable? There are also many equivalent ways to define amenability, but maybe one of the more geometrical ways to define amenability is the following. The group G is amenable if has Follner sequences. And what is a Follner sequence? It's just a sequence of finite subset of the group where the borders of these finite sets are smaller and smaller with respect to the size of the set. This is more or less the idea to understand a Follner sequence. So a sequence of finite subset of the group with borders smaller and smaller if we compare the border with respect to the size of the set. For example, the abelian groups are amenable. So which are the typical Follner sequence of the integers, for example, the intervals. So the Follner sequence are like a generalization of the intervals that we use, for example, for the ergodic theorems, all these kind of things. For groups, we can define this kind of thing using Follner sequences. And examples of amenable groups are the abelian groups. And examples of a non-amenable group are the free groups, for example, with more than one generators. And what I said before, the amenable groups can be characterized by saying that the group G is amenable if and only if for every topological dynamical system XG, the space of invariant probability measure is non-empty. And there is one side of this proof which is easy to show. This is given by the Krylov-Bogolyubov theorem. So if you assume that the group is amenable, you can define invariant measures. The other part of the characterization is more complicated, but is more or less classical. So we can characterize amenability like this. The group G is amenable if and only if the space of invariant probability measures of every topological dynamical system is non-empty. And there are, okay, when we write this, when we say that the group G is amenable if and only if every topological dynamical system has a non-empty set of invariant measure, we say that the family of topological dynamical systems is a test family for amenability. That means that if I look all the topological dynamical system and if I check if all of them has invariant probability measure, so I can deduce that the group is amenable. There are some results that show that we can find smaller test families for amenability. So for example, the result that I mentioned before, Giordano and de la Harpe in 1997, they showed that the family of topological dynamical system where the phase space is a Cantor set is a test family for amenability. So the group G is amenable if and only if every topological dynamical system with a phase space Cantor set has invariant probability measure. And we can say a little more. The family of subshifts is a test family for amenability. So amenability can be characterized in the following way. The group G is amenable if and only if every subshift given by the action of the group G has invariant probability measures. And a little more, this is a paper in the archive. The family of subshift in the 0-1 alphabet is a test family for amenability. So that means that the group G is amenable if and only if any subshift x in 0, 1 to the g has invariant probability measure. So when we see this, and we know that the residually finite groups are characterized by the existence of strongly aperiodic toplet subshifts, a natural question is to try to figure out if the family of toplet subshifts, the family of strongly aperiodic toplet subshifts, is a test family for the amenability of residually finite groups. And the answer is yes, it's possible to do that. And this is a consequence. Then I'm going to explain the general result. This is a consequence of something known as Furstenberg-Weiss almost one-to-one extension. But what can we say about this? Suppose that G is a countable residually finite group, an infinite. So the following statements are equivalent. The group G is non-amenable. This is equivalent to the existence of a strongly aperiodic toplet subshift without invariant probability measure. And a little more, you don't have to look for all the strongly aperiodic toplet subshifts. It is enough to take an odometer, so a minimal equicontinuous action on the counter set, and to look on all the almost one-to-one extension of the odometer. So the group G is non-amenable if only if for every minimal equicontinuous counter system there exists a toplet subshift, which is an almost one-to-one extension of these minimal equicontinuous counter systems without invariant measures. So strongly aperiodic toplet subshifts are a test family for amenability for residually finite groups. And I have to say that also Todor Tsankov has shown this result, but using other kind of tools. It's not published. Okay, and how can we get this? I'm just going to explain the general result. Yeah, this is just the definition of what I understand, but I almost want one extension. But what is the idea behind this? Okay, this result is a corollary of something called almost one-to-one extension of Furstenberg-Weiss type. This was an idea of Furstenberg and Weiss from '89. So what is the idea? You fix a system, Z. In this case, the system for us is a minimal equicontinuous action on the counter set. And then you take any extension of Z. And to this extension, we have a space of invariant probability measure that maybe is empty. We don't know, but there is something there. And the idea is to try to find an almost one-to-one extension of Z, X, which is related in some way with the original extension Y. And how is this relation? This relation is given by some equicontinuous, some equivariant Borel map that can be extended to the set of measure by some affine homeomorphism. And what is the story about this kind of extensions? In '89, Furstenberg and Weiss, they show that if you fix Z, any minimal action, and Y transitive, it was possible to find an almost one-to-one extension X and a Borel map from Y to X in order that this extends to an injective map from the space of invariant probability measures of Y to the space of invariant probability measure of X. Later, in '98, Donarovich and Lacroix, they just work for the action of the integer, but they improve a little bit this result, showing that it was possible to do that in order to get an affine homeomorphism between both space of measures. So they say, okay, we start from a minimal action Z. We take any extension of Z, any extension Y, and they show that there exists some almost one-to-one extension X, which is related by some Borel map between Y. And in order that this map define an affine homeomorphism between the space of invariant probability measures. So both systems have the same space of invariant probability measures. And what we did with Jaime, this is just the thing that I explained, but with words. But we did with Jaime was trying to do the same, but for residually finite groups. So we fixed for residually finite group and taking Z as an odometer. So a minimal equicontinuous action on the Cantor set. So you fix Z, a minimal equicontinuous action on the Cantor set. You take Y, any extension, any topological dynamical system, a minimal topological dynamical system, which is an extension. And it's always possible to find an almost one-to-one extension of Z, which is related with Y by means of an equivariant Borel map, and also this equivariant Borel map defining an affine bijection between the space of invariant measure. And if Y is a Cantor set, we can ensure that this affine bijection, in fact, is an homeomorphism between the space of invariant measure. So this implies, for example, if you start with a group G, which is not amenable, we know that you can find some Y here without invariant measures. The almost one-to-one extension of C is also a dynamical system without invariant measure. And from that, we can this is just the idea of the proof, but I'm going to skip here. But doing this and a little more work, we can find this X. This X in general is not a subshift. It's not a symbolic system. But doing some work, we can prove that you can choose this X like a symbolic system. And if this is symbolic, and if this is an almost one-to-one extension of an odometer, this is a topless subshift, thanks to the characterization of this system. This is just the sketch of the proof to go to the symbolic system. And I stop here. Thanks.